Hey there, and welcome. Today we are going to dive headfirst into the world of alkenes. Now, this is a family of molecules that is, no joke, fundamental to our modern world. We're talking about everything from the plastics we use every day to the fruit we eat, and it all boils down to one very special chemical feature. So, to kick things off, let's start with a little puzzle. Think about this. What on earth could possibly connect the sweet smell of a ripening banana with a simple plastic grocery bag? I mean, they seem like they're from completely different universes, right? But believe it or not, they share a secret chemical connection. And the answer is the carbon-carbon double bond, this little guy right here. This single feature is what defines an alkene, and it's the key that unlocks an absolutely incredible range of chemistry, from natural processes happening in a piece of fruit to massive industrial manufacturing. Okay, so let's get properly introduced. It's time to meet the alkenes. What exactly is it that makes an alkene an alkene? All right, here's the official breakdown. An alkene is what we call an unsaturated hydrocarbon. And the key thing is that it has at least one of those carbon-carbon double bonds. Now, that word unsaturated, that's super important. It basically means the molecule isn't holding the maximum number of hydrogen atoms it possibly could. It has room to add more, which is a massive clue about its personality. It's ready for action. You know, to really get a feel for alkenes, it helps to put them side by side with their simpler cousins, the alkanes. Alkanes, they've only got single bonds. They're saturated, and honestly, they're chemically pretty stable. You might even say a little boring. But alkenes, with that double bond, they're way more reactive, more dynamic. That one extra bond literally makes all the difference in the world. Now, here's something really cool that comes from that double bond. It's rigid. A single bond can spin around freely, no problem. But a double bond? It's locked in place. And because it's locked, it can create two totally different arrangements in space, which we call cis and trans isomers. In the cis version, the big groups are stuck on the same side. In the trans version, they're on opposite sides. It's the same exact formula, but a different 3D shape, and that means they have different properties. Okay, so we know what they are, but where do they come from? Let's take a look at one of the most common ways you'd actually cook up an alkene in a lab. It's actually a pretty simple recipe when you get down to it. You just take an alcohol, you heat it up with a strong acid, sulfuric acid is a popular choice, and that acid acts like a catalyst, helping to literally pull a water molecule right out of the alcohol. And in that space that's left behind, a new carbon-carbon double bond just snaps right into place. The whole process is called dehydration, and boom, just like that, you've made yourself an alkene. So now we get to the real heart of the matter. Why are chemists so obsessed with alkenes? Well, it all comes back to that double bond. It's not just some structural piece, it is the absolute center of the action. It's the star of the show. I love this analogy. A great way to think about the double bond is to picture it as a superhighway just packed with electron traffic, right? It has this high density of negatively charged electrons, which makes it a really attractive target for any other molecules out there that are on the hunt for electrons. And all that traffic on the superhighway leads us to the main signature reaction that alkenes love to do. It's called electrophilic addition. The name really says it all. You have an electrophile, which is just a fancy word for something that loves electrons. It comes along, it cracks open that double bond, and it adds itself to the molecule. The double bond turns into a single bond, and you've got two new atoms that have joined the party. All right, theory's great, but let's see this in action. We're going to look at some famous and incredibly useful examples of these addition reactions. This is where it all gets real. First up, we have a classic principle in organic chemistry, Markovnikov's rule. It's a simple but super powerful way to predict how these reactions will go. Basically, when you're adding something like hydrogen bromide to an alkene that isn't symmetrical, the hydrogen doesn't just add on randomly. It follows this kind of the rich get richer principle. The carbon atom that already has more hydrogen atoms is the one that gets the new hydrogen. Let's see how it works. So here are our starting players. We've got propene, which is an unsymmetrical alkene, and hydrogen bromide. Now look closely at that double bond. The carbon on the right end has two hydrogens, but the one in the middle only has one. That's the key. And here's the result. Just like the rule predicted, the hydrogen from the HBr adds to that right-hand carbon, the one that was already richer in hydrogens. That leaves the bromine to add to the middle carbon. And what we end up with is 2-bromopropane. It's predictable, it's elegant, it just works. But of course, chemistry just loves to have its exceptions, doesn't it? If you do the exact same reaction, but you just add a tiny bit of peroxide, the whole rule flips on its head. Now the bromine goes to the richer carbon, and the hydrogen goes to the poorer one. We call this the Karash effect, and it's just a fantastic reminder that in chemistry, the conditions you use are absolutely everything. And now for the grand finale of alkene reactions. This is, without a doubt, the one with the biggest impact on all of our daily lives. I'm talking about polymerization. This is the magic of how we turn tiny little molecules into the massive, useful materials that build our world. It all works like a giant chain reaction. So it starts with a special molecule called an initiator that kicks things off. It breaks the double bond of just one alkene molecule, which we call a monomer. That first monomer is now reactive, and it immediately attacks its neighbor, linking up and passing that reactivity down the line. And this just happens again and again and again, thousands of times, forming this gigantic chain molecule. And this process is just unbelievably powerful. You take a simple gas, ethene, which, by the way, is the exact same molecule that bananas release to ripen. You link thousands and thousands of them together, end to end, and what do you get? You get polyethylene, polyethylene, the most common plastic on Earth, used for everything from milk jugs to, yes, those very same grocery bags we talked about at the beginning. So, from a banana to a plastic bag, the incredible journey of the alkene is all thanks to the amazing reactivity packed into that one simple carbon-carbon double bond. It really makes you wonder, doesn't it? What other secrets are hidden in the simple bonds that build our world?